Halfway to the moon, something changes, and it's not the spacecraft this time. It's the risk. For the first time in decades, astronauts on the Artemis II mission will leave Earth's protection and face the full force of the sun. But what happens if the sun erupts at the wrong moment? Could Artemis II actually survive it? And why are teams at NASA watching the sun almost in fear, non-stop like it's a ticking clock? In this video, we break down the bigger threat, the real plan, and whether the spacecraft can truly protect its crew, or if something far more dangerous could unfold. The moment astronauts leave Earth's protective bubble, the rules of survival change instantly. Inside Earth's magnetic field, known as the magnetosphere, high-energy particles from the sun are deflected, creating a relatively safe environment even for astronauts aboard the International Space Station. But Artemis II is different. It will push humans beyond that shield for the first time since the Apollo era, placing them directly in a region where radiation is no longer filtered. That shift alone transforms space from a controlled environment into something far more unpredictable. This danger isn't constant, it arrives in bursts, and that's what makes it more complex. Solar flares and eruptions known as coronal mass ejections can release massive clouds of charged particles that travel through space at incredible speeds. According to NASA's mission data, these events can significantly increase radiation exposure in a short period, especially outside Earth's magnetic influence. Unlike background radiation, which is steady and measurable, these solar events are sudden and can vary dramatically in intensity. That means astronauts aren't just exposed, they're exposed unpredictably. What makes this even more critical is timing. Artemis II's trajectory takes the crew through deep space for several days, and even a short-duration mission can intersect with a solar event if the timing aligns. NASA experts emphasize that distance alone doesn't define risk. It's the sun's activity at that exact moment. A quiet sun means minimal danger, but an active sun can turn the same path into a high-risk corridor within hours. This creates a scenario where mission safety depends not only on engineering, but on space weather conditions that are constantly evolving. This shift from predictable protection to unpredictable exposure is the core challenge Artemis II is designed to test. It's not just about traveling farther, it's about understanding how quickly conditions can change once you leave Earth behind. And if the danger is dynamic and invisible, the next question becomes unavoidable. How do you track something that moves faster than your spacecraft? NASA treats the sun like a live threat system, constantly monitored from multiple vantage points across space. Instead of reacting after events happen, teams rely on a network of solar observatories, including missions like Solar Dynamics Observatory, to watch the sun in real time. These systems track changes on the sun's surface, identifying active regions that could erupt. The goal isn't just observation, it's prediction, and that's where things become both powerful and uncertain. The evidence shows that space weather forecasting works similarly to hurricane tracking, but on much shorter timescales. When a solar eruption occurs, scientists can detect it almost immediately and estimate its trajectory and speed. However, the warning window can range from minutes to hours, depending on the type of event. For fast-moving solar particles, that margin can shrink dramatically. NASA's monitoring systems feed continuous data back to mission control, allowing teams to assess risk in near real time. This constant flow of information becomes the backbone of decision-making during Artemis II. But here's the critical part. Detection doesn't guarantee perfect prediction. Even with advanced models, solar activity remains inherently chaotic. A region that appears stable can suddenly erupt, and the intensity of an event can exceed initial estimates. NASA experts acknowledge that while monitoring reduces uncertainty, it doesn't eliminate it. This creates a high-stakes environment where decisions must be made quickly, often with incomplete information. That uncertainty is exactly why Artemis II is so important. It's not just testing whether we can detect solar threats, it's testing how we respond to them under real mission conditions. Every data point collected during the mission will refine future forecasting models, improving our ability to predict and manage solar risks for longer journeys. And this leads to the final layer of protection. Because even with constant monitoring and rapid detection, there will always be moments when the warning comes late. When that happens, the responsibility shifts from prediction to protection. and everything depends on what the astronauts can do inside their spacecraft. Inside the Orion spacecraft, survival becomes a matter of positioning, timing, and preparation. Unlike what many might expect, the spacecraft isn't uniformly protective. Certain areas provide better shielding due to the distribution of materials, equipment, and structural design. NASA has identified these regions as temporary safe zones, where astronauts can gather if a solar event is detected. This means that during a critical moment, the crew's movement inside the capsule becomes part of the protection strategy. The mission design includes continuous radiation monitoring, both through onboard instruments and wearable detectors carried by each astronaut. These devices track exposure levels in real time, giving both the crew and mission control immediate feedback. According to NASA's planning, this data is essential not only for immediate safety, but also for understanding how radiation behaves inside the spacecraft. It turns every moment of the mission into a live experiment, collecting information that will shape future designs. What makes this system especially compelling is how it blends human response with engineering. If a solar event is detected, astronauts must quickly reposition themselves into the safest configuration within the spacecraft. This creates a scenario where seconds matter and the margin for error is limited. The Orion capsule becomes more than a vehicle. It becomes a dynamic shelter where safety depends on both design and human action. This is where the real significance of Artemis II comes into focus. The mission isn't just proving that astronauts can travel beyond Earth, it's proving that they can adapt to sudden, invisible threats in real time. Every procedure, every movement, and every data point contributes to a deeper understanding of how to survive in deep space. And as NASA prepares for longer missions, whether returning to the moon for extended stays or eventually heading toward Mars, the lessons learned inside Orion will become the foundation for future exploration. Because beyond Earth, survival isn't just about reaching your destination, it's about how you respond when space itself becomes unpredictable. Artemis II isn't just a mission, it's a turning point. It shows that reaching deep space is no longer the biggest challenge, surviving it is. What NASA is testing here goes far beyond a single flight around the moon. It's building the knowledge needed for longer missions, where exposure lasts not days, but months. And at the center of that challenge is the sun, powerful, unpredictable, and impossible to ignore. So here's the real question. Are we ready to live beyond Earth, or are we only beginning to understand what it truly takes? If you enjoyed this video, don't forget to like, share, and subscribe for more updates on space exploration and scientific discoveries. Your support truly makes a difference and helps this channel grow. Thank you for watching, and see you next time.